And now let's turn to our first talk, which will be given by Dmitry Molchanov, who is the deputy head of our laboratory here in Samsung AI Center, on very interesting topic, at least from my viewpoint, about implicit models, so-called implicit heuristic models, and their usage for approximate Bayesian inference. This is a new technique that is different from what we usually use for approximate Bayesian inference, meaning variational inference and Markov chain Monte Carlo, because MCMC, as you know, can be quite precise, but too slow in many practical situations. And on the other hand, variational inference can be quite fast, but too inaccurate to good approximate the posterior distribution. So this is a new technique that is somewhere in between two extremes and possibly could solve the disadvantages of both approaches, meaning MCMC and variational inference. We'll see in future year, I guess. So please.
Thank you for the introduction. So yes, I'll talk about variational inference with implicit models. So still these techniques are variational inference techniques, so they will be not perfect, but we will see how flexible they can become. So in this talk, I will consider two general tasks, variational inference and variational learning. So in the more general setup, consider that you have a joint distribution P of W, P of X and Z that is factorized into P of X given Z, the conditional or the likelihood function, and the prior P of Z. And next we want to find the posterior distribution over the variable Z, P of Z given X. So this posterior distribution is intractable, so we refer to the variational inference framework, which I assume you are all familiar with. So it basically tells us that if we want to approximate our posterior distribution P, our posterior distribution P, we just need to find some kind of parametric approximation Q phi of Z given X. And to find it, we need to maximize the so-called variational lower bound. I think this, they are the same, and they don't work on simple screen. Yeah, it works, but not on the screen, which is a shame. So this is the variational inference task. So where you have your variational lower bound, and you maximize it with respect to the variational parameters phi to find the best fit for the variational posterior Q. The variational learning setup is very, very similar. However, instead of trying to just approximate the posterior distribution, you also want to maximize the marginal likelihood function, P of X given some parameters theta for the likelihood function and theta for the prior distribution. So you want to approximately maximize this likelihood function with respect to theta likelihood and theta prior, and you can do it using the same variational lower bound. However, now the likelihood function and the prior distribution are also dependent on some parameters, theta likelihood and theta prior.
So, sorry, on the left side you have a function that depends on X, yes. And on the right you take an expectation with respect to X, so it doesn't depend on X.
Yes, there should be expectation over X here. Yes, and so yes, you maximize the same variational lower bound, but now with respect to both variational parameters phi, the parameters of the approximate posterior Q, and to the parameters theta likelihood and theta prior of the likelihood function and the prior distribution. So this topic is very, very broad. Therefore, I constrain myself with only one direction. So this talk is about how to perform variational inference or variational learning when your model is implicit. What implicit means, we will talk in the next slides. So this talk is not about how to apply variational inference or learning in real tasks. It is not about how to apply implicit models or where do they arise from. So this talk will not contain any fancy experiments, just rough theory. Okay, so let's go into it. So consider the more general setup, the variational learning setup. So in order to perform optimization of this objective, basically you need to be able to reparameterize your approximate posterior Q. So you need to sample from it, and then you need to differentiate through the sampling function. And then you need to compute the gradients of all these three distributions under the expectation. So you need to know the gradient of your log posterior distribution with respect to your variable z. You need to compute the gradient of the prior function with respect to the prior parameters theta prior and with respect to the variables z. And you need to differentiate your log likelihood function with respect to your likelihood parameters theta, likelihood, and with respect to your variable z. If you only want to perform variational inference and not variational learning, you are good to go with just these four gradients. So you just need to perform reparameterization for the approximate posterior. You need to compute the gradient of the log posterior density with respect to z, and the gradient of the likelihood and the prior distribution with respect to z. However, this is only the case in very simple models where we can model the likelihood, the prior, and the posterior explicitly. Explicitly means that we can compute density and we can compute the derivatives of the density. However, in the worst case scenario, when we have implicit models, none of these distributions may be explicit. So we can only sample from Q from the prior distribution and the likelihood function, and we also can reparameterize the posterior distribution. Yes?
Sorry, stupid question. Why should we have to know how to compute the derivatives with respect to z, but not with respect to parameters phi, theta, and theta?
So if we perform variational inference,
yeah.
Yes, we don't have the parameters theta likelihood and theta prior here. So the prior distribution and the likelihood functions are fixed.
But what about phi?
Yes, and so about phi we do it in reparameterization here. So we only take the gradients with respect to phi when we reparameterize Q of that given x.
But you have not with respect to phi, but with respect to z.
Yes. Reparameterization means that
Okay.
it is it can be computed and each is differentiable. So basically you have z from Q of Q phi of z given x. You can represent this as z is equal to some function f with parameters phi of x and some noise epsilon. Epsilon follows some non-parametric distribution p of epsilon. And then you need to compute the gradient with respect to phi of f phi of x epsilon. Yes. So this is reparameterization. Alright, so why would we want the models that are implicit, where we can only sample from them? So let's first consider an implicit posterior distribution. Explicit posterior distributions that have tractable density are usually way too simple. For example, the common choice is a fully factorized Gaussian distribution, which is a unimodal distribution that cannot capture the complexity of the posterior distribution well. Even if in variational autoencoders, the posterior distribution is still a fully factorized Gaussian. There is one exception, namely the normalizing flows model, which are pretty flexible family of models, and they can be considered as an alternative to implicit models, but I will not cover them in this talk because they have their own limitations. So explicit posteriors are usually way too simple. We restrict the approximate posterior to come from a very simple parametric form. However, if we allow for implicit distributions, we can just take some random noise epsilon, non-parametric random noise, for example, from standard Gaussian distribution. We can take the condition x and just plug it into an arbitrary neural network to output a sample z from the conditional distribution q of z given x. So this conditional distribution can be made arbitrarily complex using this neural transformation. So second, you can consider a model with an implicit prior. So there are several examples of models with implicit priors. So one example is when you define a model with hierarchical prior distribution that follows the following form. So you have your variables z, you have some kind of prior p of z given psi, with psi being the hyperparameters of the prior, and you have a hyperprior p of psi, and then you obtain the joint prior distribution p of z and psi. But in order to actually perform inference in the model, you need to consider the marginal prior distribution, which is the integral over psi of the joint prior, and this distribution is usually implicit.
And you assume here that the likelihood function actually does not depend on psi.
Yes, the likelihood function does not depend on psi, only the prior distribution depends on psi. So one example of such prior is the relevance vector machine model, where you have a fully factorized Gaussian conditional prior p of z given psi with zero mean and some variances alpha, and you have a hyperprior over alphas, which is a gamma prior. So this model is tractable, so this integral is a pseudo distribution, but in the general case it is not tractable. So the second possible scenario when implicit priors may arise is when you take some data, take some, for example, standard Gaussian prior, and find the posterior distribution over the parameters q of z. And then you discard all the data and you want to add some new observations into your model. In that case, you would need to set your new prior distribution to a previous posterior distribution. So you do that, you perform variational inference once again, and you obtain new approximate posterior q t plus 1 that captures the whole data set. And of course, if you want to find a flexible approximation to the posterior, you would model q of z as an implicit distribution, and if q of z is implicit, then p of z is also implicit. And finally, there are some formulations of variational autoencoders that need to consider optimal prior distributions with respect to the evidence lower bound. And you can actually show that if you optimize the evidence lower bound with respect to the prior distribution, you obtain such kind of aggregated posterior distribution. So you take a data distribution p of x, and you use it to mix all the posterior distributions q of z given x into some kind of implicit prior. So this is another example of implicit priors. Alright, and finally the most strange situation, what if you have an implicit likelihood? So usually in most machine learning benchmarks, for example classification tasks, regression tasks, your likelihood function is just some kind of parametric density, so that you can easily compute. For example, in classification, you just need to compute the cross-entropy loss to access the log likelihood function. However, there are a lot of different formulations that usually arise in practical applications, like in physics, in biology, etc., where you don't have the likelihood function. You have some kind of a black box simulator that has some parameter z and maybe some random state epsilon, and then you run this simulation with parameter z and obtain a sample of x, which is actually a sample from your likelihood function or from your distribution x given z.
Is it really a sample or just deterministic function?
It can be a random function if your black box simulation has some kind of random state. For example, if your simulation is a quantum computer, it will be random.
For example.
For example, yeah. And so the question arises how to find the parameter z, because we just cannot estimate the actual value of the likelihood function, so we can't even perform maximum likelihood estimation. Well, there is a way to do it, and I'll tell you about it next. So there are a lot of different approaches to implicit modeling. So I chose the following 4 approaches. So the first one is discrimination-based density ratio estimation. Then there are 2 different approaches that are based on reverse modeling, and finally an approach that's based on denoising autoencoders. There are many other approaches, for example, semi-implicit variational inference, which will be covered in one of the next talks. Kernel implicit variational inference, operator variational inference, but so I do not cover these techniques here. So why did I choose the following 4 techniques? Well, discrimination-based density ratio estimation right now is the most widespread solution to implicit modeling, and it is actually the most general approach. So it applies to basically any kind of models. The hierarchical variational inference approach is very simple, and it should be pretty easy to optimize. And so unbiased implicit variational inference finally feels like the right way to perform variational inference with implicit posterior distributions. And finally, I found a very unexpected and beautiful result based on denoising autoencoders on how to actually estimate the gradient of any log density just by training a denoising autoencoder. Alright, so let's start with discrimination-based density ratio estimation. So basically you have some kind of density ratio, so consider arbitrary density Q and density P of that, and you want to approximate this ratio with some kind of, for example, parametric function d of z. So in order to do it, you minimize the following discrimination loss, which is similar to the discrimination loss in generative suicidal networks. And now I will show you that minimizing this loss actually leads, so the optimum discriminator in this loss actually is equal to the density ratio. So this loss consists of 2 terms, expectation with respect to P of z and expectation with respect to Q of z. And let's rewrite them as an integral. So you have an integral over P of z, the first term, minus Q of z, the second term, and dz. And then you just say that in order to minimize this whole integral, let's just minimize the integrated function pointwise. So if for each z we have the optimal discriminator d of z, then the whole integral will also be minimized.
If the function d in the continuous class.
Yes, if the function d is in the continuous class. And if the density q and p are in continuous class, and p of z does not equal to 0 anywhere, where q is not equal to 0, then the function d is actually good. Okay, so we just take the integrand and minimize with respect to d. So let's just compute the derivative with respect to d. And we have the following form. So we have p of z over the derivative of the logarithm, so over 1 plus d of z. So p of z over 1 plus d of z, minus q of z, and then we have the nominator, minus q of z over d of z, and plus q of z over 1 plus d of z. And then we just multiply by d of z 1 plus d of z, rearrange the results, and equate this thing to 0, because it is a derivative, so we equate it into 0, and we obtain the following equation from which d of z is equal to q over p easily follows. Okay?
Is the problem convex? Is the problem concave in convex?
It depends on the distribution skew of p. So basically, in general, in deep learning, we do not concern ourselves with such questions. In this talk, there would be no strict theorems, only some kind of intuition. So so this is not an actual proof that this is the optional discriminator, this is some kind of intuition behind it. I'm sure that there are theoretical papers that make this argument more rigorous.
It seems like Neyman Pearson theorem. So,
Yeah.
Result.
Okay. And so, which task do we want to solve? We want to solve the variational learning or variational inference task, which is basically optimization of the evidence lower bound. And the evidence lower bound is no more than expectation of log density ratios. And if you have intractable distributions that you can sample from, then you just can approximate this density ratio with discriminator and then optimize, then plug the discriminator inside the evidence lower bound and optimize the new surrogate. So for example, consider the so-called, right now let's consider the basic formulation of learning of variational autoencoders. So this is the evidence lower bound that we want to maximize. So this is the expectation over data distribution, expectation over the posterior distribution, log joint density over posterior density. And we can rearrange this guy to obtain two different formulations, the so-called prior contrastive formulation and joint contrastive formulation. So in prior contrastive formulation, we just take this term here, P of z over Q of z given x, and drag it out of the algorithm and obtain the expected chiral divergence between the posterior distribution and prior distribution. Yeah, so you have the expectation over Q log Q over P. All right, and in joint contrastive formulation, you perform a similar thing, but with the joint distribution. So you rearrange the terms, you multiply and divide by P of x, which is the data distribution, and here we assume that it is a nice distribution, so that we can actually do it legally. And then we have here the chiral divergence between the joint distribution Q phi of z given x times P of x, the data distribution, and P of x and z, the actual joint distribution that we are given in the task. So this box should begin here, which is a typo. And this entropy term at the end is just a constant with respect to the parameters phi, so we can ignore it in optimization. Okay, so we have these two formulations. Basically, we have a density ratio here and a density ratio here. And so, how to perform variational inference with discriminator-based density ratio estimation? Well, we just take this density ratio and approximate it with a discriminator using the same laws that I described before. So this is the prior contrastive adversarial learning, so-called, which is actually the same model as adversarial variational Bayes, I think it is called. So you just consider the prior contrastive formulation of the variational autoencoder and plug and replace the density ratio with your discriminator. Note that here your optimal discriminator, which is equal to Q phi over P of z, it actually is a function of phi, so it depends on phi. And it is really not clear how to differentiate each with respect to parameters phi. Right? So if we want to compute the gradient of L with respect to phi, we would need to differentiate the log d with respect to phi also.
Well,
Yes?
Okay. Is your approximate posterior, so you have only implicit prior or an approximate posterior is implicit too?
So in this formulation, both the prior and the posterior can be implicit.
Okay, so what about the first term? If you can only sample, but your approximate posterior is reparameterizable.
Yes.
But does it mean that I can actually compute density with reparameterizable?
In theory, it may be possible. For example, if you have a neural, so if your posterior is Z is computed as a neural network of epsilon, yes, and epsilon follows some kind of standard Gaussian distribution, then in theory you could compute the density of Z, but it is a computationally very hard thing to do. So you need to compute the determinants of Jacobian matrices in the transformations inside this neural network, and it is computationally hard.
The middle approximate equation, you have that on the right side, depends on x, but the left-hand side doesn't depend. So you need to train the discriminator for each x.
So yes, I think so. Yeah. Or we can use an amortized discrimination, which is basically the same function. So it's discrimination that also takes x as its input. Yes.
Is it possible to somehow unite the criterion function for alpha and for learning d of z into one criterion function?
I have not seen such results. So usually you just make several updates of your discriminator in the inside loop, and in the outside loop you make the steps with respect to phi.
But it seems that you are wasting the samples in this way.
Yes, it is not a very efficient technique, but there is nothing better right now. Alright, so there is this formulation. So in this formulation you still need explicit likelihood function, but your prior distribution and posterior distributions can be made implicit, fully implicit. So how to optimize this thing? Because, well, your discriminator D is actually a function of phi, and if you have a parametric prior, it is also a function of theta prior. Well, it turns out that if you want to differentiate the expected log density ratio with respect to parameter phi, you don't actually need to differentiate the discriminator. So these two gradients are equal. So here you have the discriminator at point phi, and you need to compute the gradient with respect to phi here. And here you have the discriminator at point phi 0, which is constant, which is a fixed value. So you don't need to differentiate this logarithm anymore. So, and now I'll show it. So you want to prove this equality. And here we will use that the discriminator that you use is optimal, which is a strong assumption, but usually it is assumed. So you want to compute size derivative, you just use that the optimal discriminator is equal to the density ratio, and then you multiply and divide by q phi 0 of z given x, the numerator and the denominator. Okay, so nothing changes, we can cancel this thing out. And then we will regroup this logarithm into the first term, which is basically the right-hand side of our equation, and the second term, which is the gradient with respect to phi of the chiral divergence between the distribution q phi z given x log q phi z given x over q phi 0. Okay, so it is the chiral divergence between q, so it should be phi, q phi and q phi 0. And the gradient with respect to phi of this chiral divergence is 0 because phi equal to phi 0 is the local minimum of such collisions. Okay, and so you have that this equality holds.
So you just say that let's take a function at a local optimum and the gradient is 0.
Yes, yes, yes. And therefore you don't need to actually differentiate through this log discrimination here. So you just detach the gradients from this point and just compute the gradients of your reparameterization. And that's all. It is still not clear how to compute the gradients with respect to theta prior, because so this equality only holds for phi, not for theta. You still need to differentiate this in respect to theta. And the only thing to do it right now, as it seems to be, is to differentiate through the whole optimization procedure of the discriminator, through the whole inside optimization loop, which is possible through reverse mode differentiation, and thus obtain the gradient with respect to theta prior. So in theory it is possible. In practice I don't think anybody has done it yet, but in theory you can do it. Alright, so what about if your likelihood function is also implicit? Well, you can do exactly the same thing here. You have a joint contrastive formulation with the ratio of joint densities, and you just train a discriminator to approximate the joint density ratio, plug it into your evidence lower bound, and use the same trick to optimize it with respect to phi. So the same thing holds. You just need to differentiate through the reparameterization here. And if you need to perform variational learning, so you need to compute the gradients with respect to theta likelihood and theta prior, you just differentiate through the whole SGD optimization procedure for the discriminator, obtain the gradients. The only caveat here is that high-dimensional density ratio estimation is somewhat difficult, but this is the only way to perform variational inference or variational learning if your prior, posterior, and likelihood are all implicit. Okay, so that's basically all about density, discriminator-based density ratio estimation. Now let's talk about some other techniques. So first, let me introduce to you the semi-implicit formulation of implicit distributions. So assume an arbitrary density Q of Z that is represented as such integral of the conditional distribution Q of Z given psi times Q of psi d psi. Even if the conditional distribution and the marginal distribution Q of psi are both explicit, the integral, the marginal Q of Z may be implicit. And if you allow Q of psi be any implicit distribution, then Q of Z can also model any implicit distribution, and vice versa. So these two formulations, so the semi-implicit formulation and the fully implicit formulations are equivalent. So you just need to say that Q of Z given psi is just a delta function, and then Q of psi is your arbitrary implicit distribution, and then with such conditional distribution you have Q of Z equal to Q of psi. Okay? And what it means, so how this thing would look like, you start from some random noise epsilon, you reparameterize psi using a neural network or normalizing flow or anything like that to obtain the parameters psi, and then you use some noise epsilon hat, combine it with parameters psi and reparameterize them into your sample z. Okay? So now let's talk about hierarchical variational inference that performs variational inference in models with semi-implicit posterior distributions in the case when both q of z given psi and q of psi are both explicit. So one example of such model is presented here. So you start from random noise, you use normalizing flow to compute the sample psi and its log density, and then you reparameterize z. Okay, so your evidence lower bound would look like this. So here for simplicity, drop the p of x and the conditioning on x. So here you can assume that we have not a variational autoencoder but a Bayesian discriminative model. But everything still is the same, just the notation is a bit simpler. So you still have your expected log joint distribution plus the entropy of your marginal posterior q phi of z. And you can compute and differentiate your expected log joint density, but the problem here is the entropy term, because the marginal distribution q of z is implicit. Okay, so hierarchical variational inference provides a way to bound this entropy term from below and to obtain a looser lower bound on your evidence lower bound, which you can then maximize. So let's do it. You start from the entropy, so there is a minus sign here, which is equal. So you just rewrite q of z using the Bayes theorem. So it is q of z given psi, q of psi, or the posterior q of psi given z. And you can just add the integration of psi here because the logarithm does not depend on psi, it is just q of z. Okay? And then you can rewrite this guy as the expected log the new likelihood. So q of z given psi times q of psi, the new joint distribution q of z given psi, q of psi, and the remaining part is the expectation over q of z, expectation over q psi of over q of psi given z of a log new posterior density. So here we try to perform something very simple, very similar to deriving the evidence lower bound itself, but now on the joint model q of z given psi times q of psi. Okay? And you have this entropy term here, so this is expected minus expected entropy. And we can bound it from below by minus expected cross entropy, because entropy is less or equal than cross entropy. And the first guy stays the same, and in the second guy you substitute q of psi given z by any kind of parametric distribution R, which models your reverse distribution of psi given z. And if you maximize this lower bound, you actually can closely approximate the entropy term. Okay, because if the distribution R can model distribution Q perfectly, then the inference gap will be equal to 0. And then you just substitute the entropy term with this new lower bound and obtain the new lower bound for hierarchical variational inference. So here you have the old expected log joint distribution minus the new expected log joint distribution plus the expected log posterior, the expected log reverse distribution. And you now maximize this lower bound with respect to both the variational parameters phi of your implicit posterior Q of z, and with respect to the parameters theta of your reverse model R of psi given z.
So what are the requirements for the reverse model?
So you need to compute its density and to differentiate it. So it
And density also.
yes. So for example, if you model Q phi of z as a semi-implicit distribution with, for example, Gaussian Q of z given psi and a normalizing flow over Q of psi, you can use an inverse normalizing flow to as your distribution R.
Is it possible to calculate the density function for the
Yes,
normalizing
yes.
flow?
So the normalizing flow is a family of transformations with very simple Jacobians. So for example, if your Jacobian matrix is an upper triangular matrix or a diagonal matrix or something like that, you can easily calculate the log density.
Mhm.
So, and this is the main idea of normalizing flows. So you may use normalizing flows here and obtain a variational inference technique for a model with semi-implicit posterior distribution. However, it is not very nice because you have this inference gap here and you have no way of estimating how large this gap is. So you just need to take faith in your reverse model approximation and use this new lower bound. However, in one of the next talks, Valera would talk about semi-implicit variational inference that allows to obtain a sandwich bound on the elbow in this case and actually estimate the inference gap here in this model.
Sandwich bound?
Yes, sandwich bound, which is
What do you mean?
a lower bound on L and an upper bound on L HBI and an upper bound on L HBI on L.
So
Yes.
the upper bound and lower bound.
Yes. Yes. Yes.
And you call it sandwich.
Yes. Yes.
Why you can't just use reparameterization or like approximation of Q over Z straightforwardly instead of looking for reparameterization R theta? Like
Why can't we compute Q of psi given z?
no, why we can't use approximation of like Q over Z instead of Q over Psi?
I don't understand the reaction. Okay, so next let's talk about the extension of this technique. This is called unbiased implicit variational inference, which is a very little trick that allows you to estimate the gradients of the true evidence lower bound. So in hierarchical variational inference, you only obtain a looser lower bound LHBI, and in your IVI, you can actually compute the gradient of L. So let's consider the same formulation. So Q of Z is modeled as a semi-implicit distribution, but now Q of psi can be arbitrary implicit distribution, not explicit like in HVI. So for example, you can have such kind of computational model. You take epsilon, you put it into a neural network, which is arbitrary neural network, obtain psi, reparameterize Z, and obtain sample Z. And we can actually reformulate this model in such a way that Q of psi would be actually explicit. So if your noise epsilon comes from a nice distribution, for example, a standard Gaussian distribution that you can compute the density of, you can just say that your Q of Z is actually the integral of Q of Z given psi, where psi is the reparameterized version of epsilon, times p of epsilon d epsilon. Here should be epsilon. And each is equal to integral of q of psi of z given epsilon, p of epsilon, d epsilon. So you can compute q phi of z given epsilon and epsilon the same way. So for example, if your q of z given psi was a Gaussian distribution with some expectation psi, for example, now you just take epsilon, compute psi, and compute the density in the same way. So nothing changes for the conditional distribution, but the distribution pi of epsilon is now, first, it is non-parametric, and second, it is explicit. So without changing the model in any way, we can rewrite any, almost any semi-implicit distribution with implicit q of psi as a distribution with explicit p of epsilon. And now we can perform, for example, the same hierarchical variational inference in a model with implicit q of psi. But it is still not satisfying enough. So let us show how to actually. So this entropy term is still intractable. You cannot compute its value. You cannot estimate its value. But it turns out that you can estimate its gradient with respect to phi. So let's show how to do it. So let's start from this gradient of the minus entropy term. You have so this reparameterization. You change your q of z to p of epsilon, and you change your z to f5 epsilon. You just perform reparameterization. And then you actually just compute the gradient with respect to phi, which consists of two terms because you have dependence on phi in two places, so here and here. So first, let's assume that this argument does not depend on phi and compute the derivative with respect to the first occurrence of phi, which is just the expectation of the gradient of the log q phi of z. Plus, now we want to compute the gradient with respect to the second occurrence of phi as a gradient of, so using the chain rule, and it is just the expectation of phi of epsilon, gradient with respect to z, which is this argument here, times gradient with respect to phi of f phi. Okay? And this first term actually can be easily computed, which is, so, yeah. So this first term would be equal to 0. And this second term, well, we now just have to deal with the gradient with respect to z of log q of z.
Why the first term is 0?
Because it is the expected gradient of the log density, which is the score function estimation.
And here by the product you mean inner product?
Let's assume that everything is one-dimensional for now, because automatic differentiation would deal with it automatically. But for the sake of simplicity, just assume that everything is one-dimensional. Okay. So we have that this gradient of minus entropy is equal to such kind of product. So we can compute the gradient of f phi with respect to phi, but now we need to estimate the gradient with respect to z of log q of z. Okay. So let's do it. So let's just take the gradient of the logarithm. That is 1 over q times the gradient of q. And now we use the semi-implicit formulation for q of z. So we obtain 1 over q times the gradient of this integral. And then we move this differentiation inside the integration. So p of epsilon prime does not depend on z, so only the conditional distribution depends on z. So here we write the gradient of the conditional distribution, and we apply the log derivative trick. So you have this term 1 over q integral p of epsilon q of z given epsilon times the gradient of the log q. Okay? And now you can arrange these blue guys together and just see that it is a Bayes theorem. So just apply the Bayes theorem here and say that all these terms are actually equal to q of psi given z, the reverse distribution. And now we just obtain the expectation with respect to the reverse distribution q of epsilon given z of the gradient of your conditional log density. And conditional log density is, so we can compute it, because the log conditional density is explicit. And now we just need to sample from the reverse distribution, so we don't need to differentiate with respect to it. We don't need to estimate the density, nothing. We just need to sample from it, and we use some kind of Monte Carlo sampling to sample from this reverse distribution. So yes, we can use. So finally, we obtain with the gradient estimator for the log q of z with respect to z, and now we can put it all back together. So the gradient with respect to phi of the minus entropy can be computed in this way, where the red guy can be computed as the expectation with respect to the reverse distribution. So here everything is, but the reverse distribution is tractable. And now let's see how to sample from the reverse distribution. Well, basically, you have your joint density q of z and epsilon, and that means that you can use any kind of gradient Monte Carlo, Markov chain Monte Carlo sampler, for example, Hamiltonian Monte Carlo, which is the first observation. The second observation is that you can actually sample z and epsilon from the joint distribution, q of z and epsilon, and use it to start your Hamiltonian Monte Carlo procedure, which would mean that you start your Markov chain starting from a stable distribution, so you don't need to warm up your sampler. And so the authors of this paper say that they use only like 10 steps of Hamiltonian Monte Carlo just to decorrelate this epsilon and epsilon prime and plug it in, and it just works. So here is the whole algorithm of estimating the gradient of the minus entropy. So you first sample your noise epsilon, you sample z from your conditional distribution, then you estimate the gradient of q of z with respect to z by taking several Markov chain steps to obtain the sample epsilon prime using the pair z and epsilon as a starting point. And then you obtain some kind of sample of epsilon prime that is independent from epsilon, which you can use to estimate the gradient of log q of z with respect to z, just by using the gradient of the conditional log density. And that's it. You combine it all together and obtain the gradient estimator for your evidence lower bound. So this is a brief overview of all previous methods. So there are two general directions. One is to use density ratio estimation, and one is to use reverse modeling. So in the density ratio estimation approach is the most general approach. It can actually even allow for variational learning setup, not only variational inference setup. And in this approach, any distribution can be made implicit. The prior, the posterior, the likelihood, anything you can make implicit. So the stability of density ratio estimation may be a concern, but empirically it seems to work pretty well. And the second family of approaches is to use reverse modeling. So use some kind of reverse models to estimate or approximate the evidence lower bound. And they provide you with a pretty simple optimization problem, so you don't have this game between a discriminator and your optimizer of your variational parameters. However, it is not applicable to the cases when your likelihood function, for example, is implicit. However, I think both of these methods can be extended to implicit priors, and I think that Kirill Nekrudov and Arsenia Shuha have shown that hierarchical variational inference can be applied to implicit priors. Yeah, but I still am not sure that this setting can also provide you with a way to perform variational learning. But if you just want to perform variational inference, you're good to go. And finally, the last technique, which is not very practical, which usually works worse than discriminator-based density ratio estimation, but I think it is a very curious technique. So consider an arbitrary distribution P of z, so you can sample from P of z, but you don't have access to its density, or the log density, or the gradient, etc. And it turns out that there is a very interesting way to approximate the gradient with respect to z of this log density. So you just need to train a denoising autoencoder to denoise sample z plus epsilon, where epsilon follows a Gaussian distribution with some small variance sigma. You just need to train the autoencoder in such a way to minimize the MSE loss, the expected MSE loss. Yeah. And it can be shown that the optimal autoencoder would be actually equal to your sample, to your variable z, plus your gradient scaled by the variance of the Gaussian noise epsilon. And if you have obtained such kind of autoencoder, then you want to compute the gradient of the log density, you just compute the output of your autoencoder at point z, you subtract z, divide over sigma squared, and obtain some kind of approximation to the gradient of the log density. Yes?
This equality, does it mean that z is one-dimensional?
Not necessarily.
Because on the left-hand side we have a norm, and it is
No, it is arg minimum with respect to d.
Argument.
Yes. So the denoising autoencoder of z is the same dimension as z, and here you have, so z is the same dimension of z, p of z is scalar, so the gradient with respect to z is also the same dimension as z, and yeah, that's it. Okay, so let's prove that. So let's prove this fact. So first, let's find the optimal denoising autoencoder in this formulation. So you just start from this objective function. So you have your squared MSE loss with expectation over distribution over z, and so it should be P of z, but it doesn't matter here. And expectation over epsilon.
Here should be KL or what?
What?
It's
No, it is norm. It is norm. So you have MSE loss times the density Q.
Ah,
Yeah,
okay.
It is a bit
The
confusing.
square brackets are
Yes.
quite confusing.
Yeah. Okay, so you start from this loss, then you change the variables to z tilde, which is equal to z plus epsilon, so your noisy input, and rewrite this integral in terms of z tilde and epsilon. So you still have here so p of z tilde minus epsilon times your squared norm. So z is now equal to z tilde minus epsilon, and here you have just d of z tilde. And then you take the gradient with respect to d and equate it to 0. So, and you also do it for every point of z, just like we did with when we try to find the optimal discrimination. So let's compute this gradient. So this expectation of with respect to epsilon does not depend on d. So we just interchange the expectation and the gradient. P of z tilde minus epsilon also does not depend on d, and only the norm depends on d. And then the gradient of the norm is pretty simple, which is just 2 times d of z tilde minus z tilde plus epsilon. So 2 times the vector with respect to which we differentiate. And then we can rearrange this guy to see what d of z tilde should be equal to. So this thing should be equal to 0. It means the expectation over epsilon of p of z tilde minus epsilon times d of z tilde should be equal to, so here we divide this bracket here, to the expectation over epsilon with respect to epsilon of p of z tilde minus epsilon times z tilde minus epsilon. Okay, and then this expectation, so d of z tilde does not depend on epsilon. You can just take this out and obtain the expression for the optimal denoiser.
But z tilde is z plus epsilon.
Yes, but z tilde is a new independent variable. So, so you can consider that. So, yeah, there is no problem here.
Why?
Because you just perform a change of variables, and here you only have variables z tilde and epsilon. This is integral with respect to epsilon, and this is
Okay,
a function of
should
z
it
tilde.
be z tilde on the second row?
On the second row, okay, yes, it should be d z tilde. Right. Okay, so we have this optimal denoiser, and now I'll provide you with some hand-wavy intuition as to why this optimal denoiser is equal to what it is equal to. So let's just see that we can open this bracket and put the z tilde out, because this term cancels out. Okay? And you have the tilde minus the ratio of two expectations. So in the nominator we have p of the tilde minus epsilon times epsilon, and in the denominator we have just p of the tilde minus epsilon. So next we will linearize p to approximate these two expectations. So let's start with the denominator. So we say that p of the tilde minus epsilon is approximately equal to p of the tilde minus epsilon p prime. And then we just compute the expectation. So this term cancels out because the expectation of epsilon is 0, and you just have p of the tilde. And you can do the same thing with the numerator. So p of z tilde minus epsilon is approximately equal to p of z tilde minus epsilon p prime. So you multiply it by epsilon one more time, and you have these two terms: p of z tilde times epsilon minus epsilon squared times p prime. The first term vanishes because its expectation is equal to 0, and the expectation of the second term is equal to the variance of epsilon, which is sigma squared, times the derivative of p of z tilde. And that's it. Let's just see that your denoise is equal to z tilde plus sigma squared times the ratio of p prime and p, and the ratio of p prime and p is actually the gradient of the log density. Yeah. So I couldn't find the strict proof of this fact, but it is stated in the appendix of some obscure paper. But I think that there should be rigorous proof to this.
So
Yes.
why is it hard? Because you in the maybe previous slide you have an O small.
Yes, in the previous slide I have O small and equal sign, and in the last slide I have
So
approximately equal sign.
it looks like you should just expand your p of z tilde minus epsilon in Taylor expansion.
Yeah.
And then take an expectation that you know all the moments of normal distribution, and
Yeah.
so it should be easy, no?
I'm a little bit concerned about the ratio here, but yeah, I think it should be easy.
Because it's not obvious for me with a black problem.
So okay. So yeah, I think that's it. So there are 4 different approaches: discrimination-based, hierarchical variational inference, unbiased, implicit variational inference, and denoiser-based. So yeah. Finally, that's how to apply this to variational inference. Yeah, right. Okay, so recall unbiased implicit variational inference. So you had this expectation over the gradient of log density of Q with respect to Z, and you can just plug in your denoiser-based estimation of approximation of the gradient, and that's it. So instead of using Markov chain Monte Carlo simulation of the reverse model, you can just train a denoiser and plug it in. And for example, if a prior is implicit, you can do the same thing to approximate the gradient of the log density of your prior. And you can train the joint denoiser over X and Z to estimate the gradient of the joint density if your likelihood is also implicit. Yes, now that's it.
Okay, what about particular examples?
Now
Does it work at least for some models?
Yes, it does work for some models, which is like a two-dimensional model with 2 modes, and it works the same as discrimination-based learning. I think this approach has been applied in combination with some other approaches, but I have not seen a paper where which performs variational inference using just this approach.
Okay, what about the previous approaches, like for example for variational encoder?
Yes, there are several papers. For example, adversarial variational base. So yes, each performs slightly better than usual variational autoencoder.
Slightly better with
In
respect
terms
to what
of
terms?
respect to the test of likelihood. So I couldn't find any particular interesting results. Because there are either very simple experiments like let's take a toy dataset or MNIST and compute test of likelihood, and there are some boring numbers. And otherwise there are some very obscure papers from other fields like physics, biology, etc., which are difficult to parse. But these are the papers that, for example, use the implicit likelihood formulation.
So that's the work in progress.
Yes, yes. So this is about the theorem, not about the empirical results. Yes?
Could you please give an example, a concrete example of variational learning problem? Or what?
An example of variational learning problem?
Yeah. It's one of the first slides.
Yeah. Okay, so basically, for example, empirical Bayes can be considered as example of variational learning. So if you have some parameters of your prior distribution that you don't want to perform inference over, you can optimize the bound on the log of x given theta, where
Log of p.
or p, log p of x given z, p of z given theta, integral over dz, and you can then write your variational bound.
And so what's the problem with applying implicit variational implicit distributions to this setting?
The problem is that it is difficult to, so if your p of z given theta is implicit, so then it will be difficult to estimate the gradient of p of z given theta with respect to theta.
Oh.
Or for example, if your q of z given x is implicit, it is also not clear how to, so you cannot compute or estimate the gradient of the evidence over bound straightforwardly.
So you mean in a general setting, right?
Yes, yes, yes.
So if we have a semi-implicit formulation, we could have some parameters in the explicit part, in the conditional distribution. And is there anything that prohibits us from actually?
So in semi-implicit variational inference, yes, you can perform variational learning easily.
Okay.
But in other formulations, it is not as easy.
Yes. Thanks.
Okay,
Any
so
more questions?
So what is another way to model value the flexible pairs is, for example, one pair. Yes. So is it any advantages one or is this approach?
advantages for implicit pairs,
For some complex pairs.
advantages for some complex pairs. For example, there is a paper called VAMP.
Yeah, I asked
Right.
you compared.
Yes, and they show that if you train a variational autoencoder with a very complex pair distribution, you can actually obtain much better test log likelihood on a wide set of problems. But they used simple
They use the
explicit.
same
Yes.
inference network as for.
Yeah, so they basically model the pair distribution as a mixture of Gaussians, but you can make this pair distribution implicit to improve this even further.
Oh.
No.
So just my question was this: we have one prior technique.
Yes.
It has no implicity. It's straightforward.
Yes.
And we have this very tough way to take gradients with
Yes.
implicit priors. Why we should prefer implicit priors instead of one prior in some situation?
So, for example, if you have a variational autoencoder with implicit posterior, your WAMP prior would also be implicit because it is a mixture of implicit posteriors. Okay? Or you could, instead of taking a mixture of Gaussians here, you can consider, for example, an implicit generator that mixes the Gaussians, which would be more flexible. And I think it should provide a better test likelihood than a WAMP prior. So it is just a more flexible model.
Okay, let's thank the speaker for this nice talk.